Hello guys, welcome to this lecture. This lecture is based on Lucas theorem. We're gonna learn what is that. So like you can see in the board, like the Lucas theorem says this: if you have to count this one mod sum p, okay, and p must be a prime number, okay. So if you count this mod p, then you can count all the mi and ni combinations, and you just multiply it with each other, okay. Where m we can write is mk into p raised to k. P is a prime number, okay. Mk minus into p raised to k minus 1 dot up to m naught, okay. So this is basically the theorem. So I am going to explain the proof of this theorem, okay. So like we know that 1 raised to x whole raised to p, okay. What we can write that pc0 plus pc1 x raised to 1 plus pc2 into x raised to just a minute, x raised to 2 plus pc3 x raised to 3 plus dot up to pcp x raised to p, right? That is basically 1, and this is also 1, okay. So basically you can find this term and the last term without p, right? Without p, because like here you can see what will be there, px plus p into p minus 1 divided by 2 factorial x square, right? For every other, like you will get some factor of p, right, in the coefficient. So when you gonna mod it with p, okay, mod it with p, so every other term except these two terms, this one and this one, will go to 0, right? Because p is a factor of all these terms. So what you get is congruent to 1 plus x whole raised to p mod p, right? Okay, this is okay. So like what we can write, I just write that result, x raised to p, just a minute, is congruent to 1 plus x raised to p mod p, right? You can write it like that, okay. That's great. Now this result we need to prove that formula, okay. So like what we can write, summation of mcn, okay, x raised to n, okay. What we can write it like that, we can write it as like 1 plus x whole raised to n, okay. This is basically the binomial coefficient formula, okay, you know, okay. So this one, what we can write, it's congruent to like summation of k may be as some particular in I equal to 0, 1 plus x, okay, 1 plus x pi whole raised to mi. Why this one? We know that we can write it like that, m equal to summation of pi mi, right? Where pi is any of the prime numbers exponentials, because I already told it, right? This one, okay. So like for this one, for this one, I write it like mod p. So for this one, what we can write, this is equal to k, or just wait a minute, I'll write it in yeah, okay. Okay, so for this one, what we can write it like that, like summation of k I equal to 0, 1 plus x pi, okay, x raised to pi whole raised to mi mod p, right? Mod p that I have explained here, this one, this equation. Okay, so like after that, what we can do, like for this one also, for this part, now consider this part as an binomial coefficient. You just write it in binomial form. Okay, so xpi mi, what we can write it like that, we can write it like that, means ni equal to 0 up to mi, right? mi c ni into x raised to ni, right? We can write it like this. So this one converted into like k I equal to 0, okay, summation of ni equal to 0 mi c ni, okay, into x raised to ni whole raised to pi, right? Yeah, pi. So pi, you consider it in inside of that one. So what you get, what you will get like that only, k I equal to 0 ni equal to 0 mi c ni into x ni pi, right? Mod p. Okay, so after that what you have to do, we have to exchange these two. We can do it, right? So we can write it like that, summation of ni equal to 0 up to mi up to k I equal to 0, okay, mi c ni into x ni pi, right? This is into, okay, x ni pi, okay, mod p, right? So ni pi is what do you get? N, right? We define it there, right? ni pi is equal to n. So like you will get summation of ni equal to 0 mi summation product of 0 to r, sorry, not r, is k, mi c ni, okay, x raised to n mod p, right? So what this term basically, this one, and focus on just write a minute, yeah, this one, okay, this term is common in both, this term and this term are common, right? And this is also same, this summation. So what we can say, like this is MCN is equal to congruent to k I equal to 0 mi c ni. Okay, mod p, right? So this is the proof basically. So we need this proof to solve this question of the day. Okay, so like I'll go to the question. Like you have to find this one modulo this one. Okay, so what I have do, okay, so for finding this one we know this one locus formula, right? So what we have to find, you are given nCr modulo 1000003. okay, so we have to find this one. So how to find this one? The formula is basically like n factorial divided by n minus r whole factorial r factorial, right? But n is so large, too large. So there might be, if you do it with Pascal triangle formula or another other factorial formula, there might be TLE coming. Okay, so what we are going to do, we just use Lucas formula. So nCr mod, okay, what we can write it like that, like what is n? N is basically what? This is mod is a prime number, right? Because 100000003 is a prime number. Okay, so if n is a prime number, so we can write n in terms of that prime number, right? So how to write that? Nk into p raised to k plus nk minus 1 into p raised to k minus 1 plus dot 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 up to n1 p plus n naught, right? This was like we have seen earlier in the locus formula. We can write it we can write m as like that. Okay, similarly we can write r also like that. Okay, so r equal to rk p raised to k, p is a prime number, plus mod p r k minus 1 p raised to k minus 1 plus dot 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 up to r1 p plus r naught, right? This is the formula for r. So what we can do, like what Lucas says, like mod p, we can write it like this, right? I equal to 0 to k, sorry, ni plus sorry, just a minute. So nCri mod p, right? So he says like that. So what we can do, like we know n, what is n? So for in the place of n, like if you expand this one, what we will get? nk c rk, right? nk c rk multiplied by nk minus 1 c rk minus 1 multiplied by nk minus 2 c rk minus 2 multiplied by dot 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 into n naught c r naught, right? This is what we are getting. So for finding, like from and in n place we know n equal to nk p raised to k, okay, pk plus nk minus 1 pk minus 1, okay, plus dot 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 up to n1 p plus n naught, right? This one. Okay, so if we divide it with p, okay, if you divide it with p, that this term will vanish, right? And you will get like nk p raised to k minus 1 plus and k minus 1 p raised to k minus 2 plus dot 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 up to n1, because this one is obviously less than p, right? So p divided by n0 divided by p equal to 0, integer division. Okay, so you will get n1, but you need also you need to find n0 c, n0 cr0, right? You need to find also this one. So what you have to do, you have to call a Lucas function or recur function. Okay, you have to call a recur function n by mod or p, whatever you, n by mod and r by mod into your finding this one, right? n0 c r0. So what it will do, it will n0 and r0, how you will get, you just modulate this one, n mod m mod, okay, mod p. Okay, n modulus mod p करने से you are getting like this one, n0, right? Because every other term will contain p, right? So it's multiple of p, so only remaining quantity that does not contain p is n0. So if you do the modular operation on n0, then you will get n0 only, right? And every other term will be 0. So what you have to do, recursion of p or the sum function n by p and r by p into some nCr function, right? nCr, to finding the nCr function. So in that function, what you are going to pass, like n mod p into r mod p, right? And n mod p and r mod p, right? So this will be your optimization part. Okay, optimize, how to optimize this. So using Lucas formula we are going to optimize this. So let's go and check what we are doing. Okay, so like here we have to find nCr, and what we do, we just pass nr to the recur function. So in recur, if r equal to 0, then obviously we know nCr equal to 1, because nc0 is always equal to 1, right? This is property. Otherwise what we can do, this is basically the Lucas theorem we are applying. We are doing again, means we are solving this problem again for n by mod and r by mod. Okay, and we are passing this to the helper function. So in this helper function we are calculating the nCr part, okay, combination part. So in helper function what we are doing, like if n is less than r, then we just simply return 0. If n minus 1 equal to r, or r equal to 1, then simply return 1, because we know that there is a property nCr should be equal to n minus r. Okay, so if r equal to 1 and n minus 1 would have same value, okay, that is equal to n. So we have to return n. Okay, great. So like this is and then we have to find the factorial, because we need to calculate that this combination. For calculating the combination, we need this, because nCr is formula what? Formula of nCr, n factorial n minus r whole factorial r factorial, right? This is the nCr formula. Okay, great. Okay, so like yeah, so after that what we are doing, like we are finding the inverse value, because what we have to do, like we need to find n factorial n minus r whole factorial and r factorial, but you can't do like that, because it's giving clearly that. So what we are doing, n factorial into n minus r whole factorial inverse into like r factorial inverse, right? So for finding inverse we are making functions like inverse function, right? See, mod inverse function we are making there, and we in there we are finding the inverse value. Okay, so this is for finding inverse value we are using Fermat-Little theorem. I have explained in the previous video, right? So this is how I do that problem, and hope you all learn something from this video. Please like, share and subscribe my channel. Okay, so let me submit that. 1 second, I think. Okay, you see. Okay, thank you.